we will talk about the paraconductivity and other properties in piezoelectric plus film hybrid devices. And there is also a poster session later in the conference about few layer superconductors, to which of course I invite everybody. So what we mean by superconducting critical roundings or critical fluctuations is the effects near the critical temperature that appear in many observables that produce roundings or excess quantities due to the proximity of the transition. And this can be seen in electrical resistivity, magnetic susceptibility, heat capacity, and other properties. And of course, they are usually characterized in terms of critical exponents, which are the log-log slopes, when represented as a function of reduced temperature. So to understand these effects, the most classical framework is based on the Aslamazov-Larkin work in the late 60s and the Lorentz-Doniak generalization to layer superconductors that produced this very well-known expression that you can obtain on the basis of the Gisborne-Landau approach with small Gaussian fluctuations. And as you see in these two figures, the agreement is quite good in a certain temperature range that comprises reduced temperatures from 0.02 to 0.1. So these figures are well known. But if we represent, well, this is for IPCO, optimally doped, this is for LASCO, overdoped, but if we represent the same as just plotting the resistivity versus temperature, we see that this approach really works very well in the transition, but there are obvious problems if we go up in the transition or in the tail. So the agreement is certainly not complete. So let's talk first about the high temperature region. There, what is seen is that the fluctuations actually go to zero much faster than predicted by the theory. The theory, the Aslamazov-Larkin theory, will be the dotted line. Normal state background will be this slash line, and you see that the data really go to the background much faster than predicted by the theory. If you express this in terms of the log-log slope and you extend it to lower temperature, you see that there is a very, very drastic drop of the fluctuations, faster than any power law, in fact. So to explain this effect, we proposed from Santiago de Compostela that this is actually due to the limitations imposed by the uncertainty principle when you try to do a fluctuation that is smaller than the coherent length at t equal to 0. This can be expressed in terms of a total energy cutoff approach in the Gaussian-Gisborne-Landau approaches. And as you see, the agreement with experiments is actually good with the resulting expressions for that theoretical approach. Even if you write down in terms of the log-log slopes, if you extend that log-log graphic to high temperatures. So another aspect is the tail of the transition, and for that you have to consider two effects. One effect is the randomness of the distribution of dopants in these materials that naturally leads to a distribution of critical temperatures that fortunately you can measure using the Serofil-Cool magnetic susceptibility that gives you a very direct way of obtaining the distribution of critical temperatures. And then there is the very famous Kosterlitz-Thouslis transition that happens in the tail. That the Kosterlitz-Thouslis transition temperature, you can actually measure it rather easily just with the voltage versus current curves. When you see the appearance of non-ohmic effects, if you have a slope here of 3, there is a famous result by Halperin and Nelson identifying very precisely that that temperature with the occurrence of the constant resultant transition. So with this taken into account, you obtain this beautiful, nice agreement of experiment and data. Also, a new study is what happens with the superconducting fluctuations in few layer superconductors. There is a poster later in this conference. By few layer superconductors, we mean those composed by 6 layers or 10 layers, etc. And well, as we will demonstrate that poster, there are interesting effects to be taken into account there, so I invite everybody to pay attention to that one. Let us consider now a related but different system. It's actually a device, a superconducting device. It's an hybrid device composed by a piezoelectric substrate, on top of which we grow a high temperature cuprate film. So let's study there the paraconductivity and other properties. So these systems are actually like in these representations. You start with a substrate of a piezoelectric substance. For instance, typical is PMMPT that you can find commercially in single crystals, and you grow on top of it a high TC superconductor like, for instance, IPCO. Then you make some lithography in the superconductor so to be able to apply certain electrical contacts. And there are two types of contacts. You apply a transversal voltage and you apply a longitudinal voltage. The transversal voltage you apply to the piezoelectric so to change the size of the material on demand just by changing this piece of voltage. So that produces a strain on the superconductor that it inherits because it is grown on top of it. Then the electrical contacts in the longitudinal direction and just for measuring the resistivity in the superconductor and check if it changes. Now all the credit is due here to the Dresden group by Trommler and co-workers, who were actually the people who first made this type of devices, and they study and characterize these systems very well. And what we are doing in our group is just, of course, reproducing these materials, and we ask about what are the superconducting fluctuations and the paraconductivity in these devices, taking a view of the question that does on-demand strain offer new experimental opportunities to understand paraconductivity, or to grow these films over PMMPT is not very different to grow over strontium titanate. The crystallographic unit cell lengths are quite similar. We do that by cathodic sputtering deposition. One has to take into account that one needs a growing method that does not exceed 800 K, because otherwise there is a phase transition in this type of substrates. But one takes that into account, one obtains films with very sharp transitions, quite standard when you do not apply the the piezo voltage. So how do you measure the strain you are producing when you do apply the piezo voltage? Well, you may put a strain gauge above the sample. This was the method used by the Dresden group, and you measure with that in-plane strain. What we do is we rely more on X-ray crystallography. So what we do is X-ray diffractograms at cryo temperature. So we cryogenize the sample space, and as you see in these peaks, you can actually see the displacement of the peaks as you apply the piezo voltage, and this gives you both in plane and out of plane strains. And you soon discover, for anyone wanting to reproduce these experiments, two experimental warnings. The first is that the process has hysteresis, the piezoelectric has hysteresis. So decreasing and increasing the field, you have to take that into account. Fortunately, as temperature decreases, the coercitive field increases, so there is an ample region in which the system is just linear with no hysteresis, so that makes things much easier. And the other warning is that mechanical relaxation is not instantaneous, it takes minutes. So we wait at least 20 to 30 minutes until relaxation is stable. What we are going to study in these systems is what we call piezo paraconductivity. The piezo paraconductivity is defined as a direct subtraction of two measurements. So it is the resistivity, well, the conductivity when you apply piezo voltage minus the conductivity when you don't. So this has the benefit of not having a background, which is very useful in critical phenomena. So we have an expression for this paraconductivity using the conventional Aslamazov-Larkin framework. This was done by Jose Verde, a student of us during a stay at Urbana-Champaign. You can actually introduce the piezo stress in the Gisborne-Randall energy spectrum, and then you apply the framework of Aslamazov-Larkin to obtain a contribution that is proportional to the piezo electrical field. So you measure that. For that, you obviously have to measure the resistivity at the transition with different electrical piezo voltages. So you have a very slight change of the critical temperature. Obviously the change is very small, but you can actually measure and you can obtain this piezo conductivity, and you get a surprising result. That is that the experiment is actually much larger than the expected piezo conductivity. So fluctuations at first sight, they seem to be quite exotic in this material. Both the amplitude is very different, and also the critical exponent is clearly different as well. So this is for different piezo voltages, and obviously you still have that, well, the experiment clearly is not in agreement with conventional theory. Okay, in order to understand these possibly exotic fluctuations, one first has to see that there are also large piezo resistance far above the transition. So if you measure far above the transition, you obtain the variation of the resistivity with the piezo voltage, and you obtain this piezo resistivity that is quite large when compared to many other materials. And the origin of this effect is really not clear. It was measured also by the Dresden group, so it's still not a well understood effect in spite of being measured several times. Some possible reasons for this non-zero normal state piezo resistance may be the geometry variations, just the change in resistivity due to the simple change of the size, but this, if you make estimates, is one order of magnitude below the observation. It could be also an effective variation of the mean free path. It's a quite similar effect to the size variation, but this time of taking into account the mean free path. But this again is one order of magnitude smaller than that what is seen. One could also think about the possibility that if you change the size of the unit cell, then maybe you are inducing a change in the doping level. But it has the mystery that if you see how much the critical temperature changes and you translate that to a change in doping, then this also produces one order of magnitude smaller effect than what is observed. So this is not really a very good explanation to my knowledge to this effect, but the fact is that it's a normal state effect that is there. So we should include that effect somehow in our expressions for the fluctuation effects. And for that, we observe that this piezo resistance remains essentially constant with temperature until very near Tc. So you see that at these two temperatures, the piezo resistance is almost the same until you actually go very close to Tc, then it becomes way larger. So what we have done is to include that regular contribution into the expression of the paraconductivity. This should be in principle proportional to the piezo voltage. And we just check what happens if we include that regular contribution. And yeah, if you do, then you obtain a much better agreement with experiments, as can be seen. And therefore, our conclusion with these systems is that they exhibit a piezo paraconductivity that is much larger than expected at first, and that can be accounted for by introducing an additional regular contribution to the usual Aslamazov-Larkin predictions. And that's the end of my presentation. Once again, I am very sorry for this format of presentation in video, but well, apparently it's not so easy to fly from Spain to Turkey, and the flights get delayed, and that's the only option we have. Thank you again. Please do not hesitate in contacting me by email or in the next days, because I hope to be able to finally arrive there. So thank you again to everyone.